We start today with the program DC Slope for the slope stability and slope failure analysis. And if we start the program first, we have some standard cases offered where you could just select one of these cases and enter the measures, height of the slope, inclination, and so on. But at this time, I would like to start with an empty project to show all the input functions for this analysis. As in most of the programs, you have the most important functions under the icons at the left. And at first, we have the selection of the analysis standard, where we can select, for example, Eurocode 7. And we have quite a number of national annexes predefined, like Germany, Austria, France, Great Britain, Italy, and Spain. And you might define a free type of analysis where you can define any national annex, for example, Czech Republic or whatever you need to use this local settings for the Eurocode 7. In addition to Eurocode 7, we have two older German standards, and we have the Swiss standard SIA 267 available for selection. And if you select one of these standards, all the parameters are predefined. So where to use the safety factors, for example, on the loads and on the layer parameters, soil layer parameters, or the resistances like passive earth pressure. And then we have the different safety factors. In Germany, for example, we have different design situations for permanent, temporary constructions or extraordinary loads. And we can just use these predefinitions for the analysis. Now, first for the ground surface, we can define any, like a polygon, the ground of this slope. So by clicking with the left mouse button, we add additional points. And we finish this function as it is shown here at the status bar at the bottom with the right mouse button. And then the program asks for the first soil layer. And we can enter the parameters directly, like angle of internal friction, cohesion, unit weight, and so on. Or we can use a parameter suggestion where we can predefine a number of soil types which are used again and again. So if we use sand dense, for example, we have a predefined friction angle of 35 degrees, cohesion of 0, and so on. And we can use this suggestion instead of typing all the parameters. Now, if we use a name of the soil type which is available in the program, it may be filled with a specific color. So this means this soil layer name is an arbitrary text. You can enter any text as you like, but if this text, this name is found here under settings in the symbol editor, here we have a large number of predefined soil types. And for example, we can see that gravel is by default shown in yellow, sand in orange, and so on. And if the soil type that you entered is found in the abbreviations or in the long text, then the soil layer is shown in this color. Then for additional soil layers, we can also draw them with an arbitrary line. What we can use if we want to have a horizontal soil layer, for example, we need the right intersection with a slope here. And this can be done by the program automatically. That means if we just enter a horizontal line here, and finish this input again with the right mouse button. So this should be some gravel, for example. Then this line is lengthened automatically and is intersected with a slope. So we have the exact intersection here. And then the soil layer is following the ground surface. This input function is active as long as this icon is pressed here. So you see, with the pressed icon, we enter a new soil layer again and again until this function is finished. And we finish that with the right mouse button, so that this icon is not pressed anymore. And then we switch from input mode to edit mode. That means that I can select any element, any soil layer, for example, which is shown in red. And by double clicking, I can change an available soil layer. So if we stop the input functions, we are in edit mode, and we can edit and change any element shown here on the screen. We can as well take a point and move it to any other position. We can double click any point and enter the coordinates and so on. And if we have the ground surface and all the soil layers, we can then define, for example, water level. We can have artesian water pressure, and we have different types of elements. I will show this later. First, if we want to start the analysis, we can define a specific friction circle by clicking the center and the second point. Then we have the center and the radius for one specific circle. And now we can tell the program to iterate the center of the circle and to iterate the radius to search for the minimum safety for the slope. So we have this starting circle. We can calculate here with this icon. Then we see the red crosses here. The centers are iterated and the analysis is finished. And now if we look at the graphics here with this pen icon, we want to label all analyzed friction circle centers. We have a certain scale which is matching into our sheet, the defined sheet for the graphics. And then we see one special effect which is typical for the friction circle for the method of Krey-Bishop. That is, we have just a very, very small area breaking from the slope surface, which is a typical effect if we have a cohesion of 0. If we have only a friction circle, and if the soil would in reality have a cohesion of exactly 0, this would be the first little block sliding from the surface of the slope. But in reality, there is no soil with a cohesion of exactly 0. So we always have at least a very, very small cohesion. So if I go back to the input window here with this arrow icon, and I double click the soil layer, and I enter a cohesion of only 0.5, which is nearly 0. And as well, this soil layer might have a cohesion of 1, for example. And we calculate again. And look at the result. Then we have a much better friction circle, which is more what we expect for a friction circle of a slope. Now we just iterated starting from a first circle. There are just a number of different functions for for the iteration and for searching the minimum safety. So just to show a special example, if we have a building here on the ground surface, and let's say we would start with a little smaller circle here, and there would be a building here on the slope, and this building may act with its weight. So we have a very high weight of 2000 kilonewtons per meter slope, and such a building cannot be cut by this slip circle. So if the circle would go through the building here, we would have an infinite safety, but we expect now that this slope would break here around this building. But if we start with one special circle and only iterate from the center and from this defined radius, we have the effect. Okay, this is not what I wanted to show you first. I'm starting with a different circle to show you a special effect for the analysis. For example, if we start with a smaller circle here in the slope, and then we are still in the slope for the critical friction circle with an utilization of 0.8. So in this case, the program would not find a circle going around the building, which is expected due to this high weight of this building. And so for this kind of effect, if we have large steps or jumps in the safety factors, we have additional functions to calculate a larger area and to completely cover this area of this slope and building. And so we can define here a grid of centers. And so we tell the program to calculate this complete area and calculate all these centers for different friction circles. And in addition, here at one point we are very far from the surface, at another point we are very near to the surface. So we also should calculate a certain range of radius. So not only starting from a fixed radius, but for example, we want to calculate from 1 to 20 meters, all these values for the radius of the friction circle. And if we calculate this, the program searches for all this area and then does a refinement. And if we look at the result now, we have what we expected. We have a friction circle just going behind the building with a much higher utilization. The previous one was 0.8. So this is the critical friction circle spanning over the building with its high weight located on the slope. So if there are big jumps, for example, here we have a utilization of 0.8. Here we have an infinite safety. We can't cut the building. And on the other side, we would have just a high utilization. So we have to make sure that all this area is calculated and all the radius covering the circle in front of the building and behind the building. So this should be calculated as a whole. So far for this effect of the building weight. If I delete this building, this is done with clicking with the left mouse button and using the delete key. then we would have the circle in the slope. And now, just another example, if we want to have a friction circle covering the complete slope. So the slope is fixed, for example, by some shotcrete wall or whatever. We can define an element called component. This might be a sheet pile wall, or this might be a shotcrete wall here on the slope. So this is covered by shotcrete, and we have a shear resistance of this element, for example, of 500 kilonewtons per square meter, which is about the shear in a non-reinforced concrete. And this element has a width of 10 centimeters and should support the slope here. So if we calculate again, the program does the iteration again of all this grid and the radius area, and in the results we see that now the complete slope is covered, because if we cut through this component, through this element, we have a much higher safety, and the critical friction circle is now going just around this shotcrete wall with a utilization of 0.84. So we can use different kinds of elements. We had the building, we had the component. There are special elements like stabilization columns supporting a weak cohesive ground under a dam, for example. We can use anchors for stabilization. We can define different types of loads, concentrated loads, distributed loads. And we can also change the width of the lamella of this friction circle, which is by default created automatically. There might as well be a fixed point. So to define that, for example, a friction circle should always go through the base of the slope, and then it is not iterated freely, but always is going through this specific point. This is the calculation with the friction circle by the method of Krey-Bishop. And we have a second method to be used in this program, which means we have an analysis according to Janbu, where we can combine straight lines and arcs of circles. We have to decide which method to use. So if we have a friction circle entered here, we cannot use the Janbu method. So if I delete here the grid and the circle, and also delete this component, then we have the other methods activated here. So we can define, for example, here a straight line and arcs of circles. Now it makes sense if we have a straight line to add the circle, the arcs of circles, as a tangent to the line, and this is possible by entering the straight line first. It should be here in this area, and then the arcs of circles are added at the endpoints from here to here, and this gives automatically an arc of circle where we have a tangent to this straight line, and the same here at the other side. And we can calculate this type of friction area, and this, for example, gives a little smaller utilization than we had before with 0.8. For this kind of area, of friction area, we have or it is quite complex to make an iteration for finding the minimum safety. So if we have only straight lines, we implemented a different optimization methods. So for example, I delete the circles first, and I make an approximation by straight lines only. So this should be a sliding block like this. And again, different straight lines at the other side. So we have only straight lines combined. And in this case, we can use a very specific optimization method, which is called particle size optimization. And here the programs automatically creates many different lines and is trying to follow a path to the minimum safety. So we can activate this particle swarm optimizer, which is abbreviated as PSO. There are many options to use. You don't have to change them because these are parameters which are quite optimized. But if you want to go in detail, you may change the different parameters here. And if we calculate this method with PSO, this number of lines is used. So we have 1, 2, 3, 4, 5, 6 lines, and it's iterated. And if we look at the result here, the program found a sliding block which is a little similar to a friction circle, but not exactly a circle. And here we have a higher utilization, which means a lower safety factor as a result than we had with the friction circle with 0.8. So this special optimization method found a safety lower of the basic iteration of the friction circle. So to follow the analysis in detail, we have result output, where we enter or where we show all the input data, and this should be set to English here. So we have the soil layers, we have the coordinates of the soil layers, lamella, safety factors. We have the sliding plane, which was defined, and the parameter of the optimization. For the English output, I have to calculate again. And then we have the resulting failure plane and the calculation of all the lamella elements, which are leading to this utilization factor of 0.91. So far for DC slope, we had 3 methods: Krey-Bishop with a friction circle, Janbu with straight lines and arcs of circles, and the special optimization with the particle swarm optimizer for this type of only straight lines combined in the ground.